this idea of elementary row operations, which most of you are familiar with, but what essentially we will do is try to see what these matrices would look like, in particular this Aij alpha matrix. Okay, this is crucial because it would be utilized extensively in a class of matrix decomposition problems, which we are going to take up next. So let us take the most complicated form to begin with. Let's consider a matrix, say M, which is say 1, 2, 3, 4, 5, 6, 7, 8, 9. And when we are doing this operation, say E1 to minus 1. Okay, the task of this operation essentially involves so row 1 becomes row 1 minus, okay, so plus of minus 1 times row 2. Okay, so this minus 1 has a connection to this minus 1 that we see. The second index has a connection to the index of the row to which we are adding, and this 1 is essentially our row 1. Okay, so like basically the end of this operation, like if we are saying E1 to N, so saying 1, so that is minus 3, 2 minus 5 is minus 3, and 3 minus 6 is minus 3. Root, and this becomes same. What is going to be E2? Okay, so here it is not even 2, but E1 minus 1. E1 to minus 1. So what is E1 to going to be? So it is going to be, to begin with, an identity matrix of the same order. So basically, if it is 3 by 3, it is going to be a 3 by 3 matrix, identity matrix. And then in the 1, 2 element, that is first row, second column, I'm going to put a minus 1. And that is what would be the definition of E1 to minus 1. So again, it is E1 to minus 1. So that's okay. Like suppose we have a matrix like EI alpha. Right. So suppose we had to write this, you can, so in the previous case, you can check that if you multiply this E1 to minus 1 with M, you actually get the result which is there in the second line. So you are going to get this, provided you will have a product of, so basically E1 to minus 1 would be 1 minus 1 0 0 1 0 0 0 1 times this thing 1 2 3 4 5 6 7 8 9. So that's going to lead us to the corresponding result. Okay, so it's fairly straightforward, like once you know how to do it. So I will be asking you a simple task of practicing or trying out on your own, it's not very difficult. What is, say, E23? What would be this? And what would be E, say, 13? So where we are exchanging this rows, like, so row 1 becomes row 3 and row 3 becomes row 1. So that is the corresponding matrix would be E13. And that's also in a sense is called a permutation matrix. And E23 is like you are scaling the row 2 by a factor 3. Right, so that's another part. Let's just, I guess somebody was in the lobby, looks like. Just add. What happened to him? He was already in the room. Fine. So from like these kind of matrices would be useful. So as and when we require them, we will write them. So let's come to this idea of matrix decompositions, which we started last time, but could not really complete. So matrix decompositions are core to linear algebra. So you would see that a lot of algorithms that come out of linear algebra, like their efficiency depends on the matrix decomposition techniques that we use. So basically, to make a particular calculation more time efficient, you would like to do a particular type of matrix decomposition. So we will see some of these later on in this course. And these matrix decompositions have had proven efficacy in diverse areas, like from bioinformatics, where one is trying to handle human genome, like in machine learning problems, in ab initio methods in quantum mechanics, and so on. So these matrix decompositions are core to many of the calculations which go inside the computer codes, right, for solving such problems. So one of the most famous decomposition problem is the Lu decomposition problem, where A is a square matrix and one needs to write it as a product of two matrices L. As the name suggests, L is the lower triangular matrix where Aij equals to 0 for all j's greater than I. So all the indices are greater than the row indices. So low triangular matrix L could have been, say, 1, 3, 4, -2, 1, 0, 0, 0. So some of the elements in the lower triangle can be 0, but all the elements in this region must be 0. That's the requirement for a lower triangular matrix. And similarly, an upper triangular matrix could be, say, again, the diagonal elements need not all be non-zero. So some diagonal elements can also possibly be 0. But now in the upper triangular case, all the elements below this diagonal are going to be 0. And some of these elements have to be necessarily positive or negative, but non-zero. And it can also be 0. So this could, like this 0 that we are writing in the second row, third column, could have been a non-zero quantity or a 0 quantity. But what is essential is all the Aij's for I greater than j have to be 0 for an upper triangular matrix. So we will try to understand this decomposition problem. How do we do it? Using the following example. So let's consider a matrix A which has the following components as 1, 0, 1, 1, 1, 1, and 2, 2, 1. And what we want to do is want to convert it into an upper triangular form, that is a U matrix. And for that, we are trying to use this elementary row transformation. So what you see is first you apply a transformation E21 minus 1. So the corresponding matrix, if you see for this, E211 is going to read like 1, 1, 1 here. And second row, first column is going to be a minus 1. The rest, every element is going to be 0 here. You can check for yourself that if you apply this matrix written in red to A, you will get whatever is this one. Okay, it has the same task as mentally calculating E21 minus 1. So the next task is now we need to eliminate this say third row first column, so 3 1. So in order to eliminate that number, what we can do is we can simply multiply the first row by minus 2 and add it to the third column. So that will lead us to the matrix which is going to look like 1 0 1 0 1 0 0 2 minus 1. That is this matrix. And in this case, the transformation matrix is going to look like again a 1 1 1 along the body diagonal, and the 3 comma 1 element is going to be minus 2, and rest all are going to be 0. So from here now we need to only eliminate the 3 comma 2 element and make it 0, and that can be done by simply using a row transformation E32 minus 2. So here what we are doing is we are multiplying this specific row with minus 2 and adding it to the third row. So that will essentially make the third row into a 0 0 minus 1, and we get our U matrix. So essentially what we have done is we have multiplied A successively by the matrix E21 minus 1, E31 minus 2, and E32 minus 2. And in this case, again, it makes sense to write down or find out the corresponding matrix. And you can again, I am repeating this again and again verbally just to make sure that it is etched out. So 3 comma 2 element is going to be minus 2, right? And then remaining are third row, second. There's nothing like that. Yeah. So now we know that if like we are multiplying, pre-multiplying A by a certain matrix. So one of the ways to get back A is to multiply by inverse of this set of product matrices and to both the sides. So basically on the left hand side you will have an identity times A, which is A, and on the right hand side you will have inverse of these quantities E32 minus 2, E31 minus 2, and E21 minus 1, and that applied on U would lead us to A. So therefore our required L matrix is going to be E21 minus 1, E31 minus 2, and E32 minus 2. So that's like equivalent to we have 1 1 1 0 0 0. We want to take an inverse of this, and this is 2 comma 1 element was minus 1. Then we had a 3 comma 1 element was minus 2, rest are 1 1 1. And then the third is 3 comma 2 is minus 2, so 0 minus 2 1 1 1. So one way to do this like matrix multiplication is to do a brute force inverse estimation. So one of the techniques which you learn in +2 is to find the adjoint matrix. So basically the minors and cofactors you will estimate, you will find the determinant, and then for a matrix A, the inverse is going to be 1 over determinant of A times adjoint of A. But it turns out for matrices where you have a 1 along the body diagonal and a typical number somewhere floating around in one of the locations. So the inverse of that is simply going to be 1 0 0 1 1 0 0 0 1. So what we are doing is we are simply changing the sign of the -1 in the second row first column. So, and similarly, the second one is going to be 1 0 0 0 1 0, and this is going to be 2 0 1, and the third one is going to be 1 0 0 0 1 0 and 0. Now again there is a sign change. This is going to be 1. Third step is to multiply these quantities. However, in this case, again, because there are 1 elements, one of the shortcut methods is to simply ensure that whatever was there along the body diagonal stays as it is. And now you have whatever are the elements which are left, you simply write them here. So this is going to be your L matrix. Let us just see, some people have again shifted to, Rajkumar is managing to shift to lobby all the time. So this is going to be our L matrix, and you can simply check LU is going to be 1 1 1 1 2 2 0 0 0, and U is going to be, U was something which we obtained, which is 1 0 1 0 1 0 1 0 1 0 1 0 0 0 minus 1. So that is what was U. Okay, so therefore this thing can be, I hope everyone knows this matrix multiplication. So you basically multiply first row with first column to get the A11 element. So this is going to be 1. The next one is going to be 0. The third one is going to be again 1. And this one is going to be 1. This is going to be 1. And this is going to be 1. Right? And then the third one is 2. Then it is 2 again. And then this is going to be 2 minus 1 is 1. So you have 1 0 1 1 1 1 2 2 1. So that is what was our A. So therefore this is equal to A, and we have implemented Lu decomposition. So the thing that we have to be careful when doing Lu decomposition is that this is possible only when A is a square matrix. This technique will not work for a M, so will not work if the rows and column numbers are different. So that is what has to be kept in mind for Lu decomposition, and that's why we need to explore some other decomposition. So the next task which I would like to do is try to kind of continue on these lines and show you that. So basically what we'll do next is this. Okay. So the next part, we can call it as spectral decomposition.
Hello, sir.
Yes.
Sir, I think one more condition should be added in this Lu decomposition.
Okay. And
So
that is,
the condition is that all the principal diagonal element should not be 0.
all the principal diagonal elements should not be 0.
Yes, sir.
That is because the pivot would go like in the denominator.
Yes, sir.
And okay, so we'll come back to that. We'll come back to that in due course. Okay, because I need to confirm the exact conditions which have to be there. Like would it be in the diagonal corresponding diagonal matrix or in general for any matrix? Okay, so we'll come back to that part. So the next decomposition that we are going to look at, we can call it a spectral decomposition, and this has deep connections to quantum mechanics. Like, so therefore, like, it is kind of relevant. And let's consider for this a real symmetric matrix S. So if S is a real symmetric matrix, it simply implies that S transpose is going to be S. That's one thing, and that is, one can say that Sij equals to Sji. Fine. And what we do is we consider a kind of orthonormal matrix I could have called it orthogonal matrix, but let me call it orthonormal matrix for reasons that will become clear. So when we say orthonormal matrix, it basically means that Q transpose is going to be same as Q inverse. And if we have this column vectors QJs, so if this orthonormal matrix is represented as Q1, Q2, Q3, and so on. So these are respectively the column vectors. Then Qi dotted with Qj is going to be 1 or 0. So basically 0 if I is not equal to j. So let's select all this. Otherwise I will not be able to. So Qi dot Qj is equals to 0 if I is not equal to j, and equals to 1 if I equals to j. And that's why I prefer to call it orthonormal matrix, but you will find in literature where this would be also called orthogonal matrix. So now with this, what we next consider is for the matrix S, if there is a corresponding diagonal matrix, say is going to be lambda, such that lambda is essentially all the elements here and zeros everywhere else. So I'm writing big zeros, so that is just to save something on writing. That means all the other elements are 0. And like What it means is like Q's are, Q is an eigenvector. S such SQ equals to lambda Q. So we saw in one of the previous classes that corresponding to the eigenvector, whenever we were multiplying the eigenvector with the matrix, it was just scaling and the scale parameter was lambda. Okay, so in this sense, you will have to look at this. So therefore, SQ, if we say, would be like S times this Q1 n equal lambda 1 Q1 lambda n Qn, and this you can write it as a matrix product in a way that you will have the Q1. Of course, you have to have this understanding that these Qj's are not like column vectors. So of course, you have to understand that Qj's are column vectors and lambda j's are numbers. Okay, so you can write them as Qn and multiply that with the matrix with lambdas along the body diagonal and 0 everywhere else. Right, and therefore this is simply written as Q times lambda. So that is equals to lambda, and what we do is multiply both sides by Q inverse, which is equal to Q transpose, because these are orthogonal or orthonormal matrices on the right. So that will imply that you will get SQ Q inverse equals to Q lambda Q inverse, which is lambda Q transpose, and that will write as S equals to Q lambda Q transpose. So this is the spectral decomposition, and the result is also known as the spectral. So translated in the Dirac bracket notation is equivalent to writing S equals to, so we have a lambda some index, say I, and corresponding to lambda I, whatever is the eigenvector, we take the outer product of the eigenvector and sum over all of them. So like it's easy to see that both these results are identical, and this particular form is very relevant in quantum mechanics. So this essentially gives us, in a way, the operator, like if you apply, for example, this operator on an eigen get lambda 2. So that is going to lead us to a lambda 2 multiplied by inner product of lambda I lambda 2. So only for I not equal to j, like these numbers are going to be 0, and for lambda I, like I equals to j, lambda I dotted with itself is going to be 1. So therefore what you would be left out is like, for example, if we apply this S on, for example, if we apply this S on 5, so that is equivalent to sum over I lambda I lambda I lambda I lambda 5. We know that for I not equal to 5, 5, this is going to be 1 if they are orthonormal kets. So therefore what it do is simply project out the eigenvalue. So in a sense, like, this is the particular form in which we would like to reduce our Hamiltonians for the problems, right? So that's very useful. So now let me just add some pages because I wish to do a couple of more things. This is edit. I don't know why it is not showing up. Okay, let me see. Or shall we just wait? Yeah, we'll just wait and try to find out. I would like to edit it. Then I would like to add some pages. So towards the end of this set of classes, I would be sending you this handout. I'm not sending it just because it's not useful to duplicate the handouts with the initial pages in place. So we'll be sending you maybe in another one lecture. So that second part, whatever we did just now, was called spectral decomposition. Now we'll do a very interesting problem. And that problem, let us call it, because this will introduce another concept called the reduced echelon or row echelon form or row reduced echelon form. So we'll see what we mean, and let us call this as CR decomposition. Okay, and to begin with, let's consider a matrix. So I would try to illustrate this process via an example, and like would be sending you a consolidated sheet with all these problems so that all that could be practiced. Let's just construct some typical arbitrary matrix, a 2, 3, 1, 1, 4, 3, and 0. Here I would put a 5. I would expect everyone to observe this matrix carefully and tell me what should be the rank of this matrix. What should be the rank of this matrix? So can I ask Mukesh? Mukesh, can you tell me what should be the rank of this matrix? Let's consider, let B. Mukesh, can you unmute yourself and tell me what is the rank of this matrix?
Sir, I at that time I not remember my
Okay,
matrix rank. How to find?
Don't worry. that's fine. So Dimple, can you tell me what should be rank of this matrix?
2.
Yeah,
Two,
that's
sir.
okay.
Two.
That's okay. Don't worry.
Two.
Don't worry. 2. And why do you say 2?
Because determinant is 0. So we can say that
Determinant is 0, but then the rank could have been 1 also if it is 0.
yes, sir. But we can.
And who is speaking right now?
Rishabh
Who is
Sharma.
speaking right now? I asked him. Hello?
Rishabh, sir.
Yes.
Hello, sir.
I see. I see. Okay, go ahead, Rishabh. But I asked Dimple. Maybe that was not audible. Huh? Okay.
Hello?
So you were saying that the rank is
Hello,
2,
sir.
but the rank could also have been 1.
3.
Right? Yes.
Yes, sir. Yes, sir. Because if we go through the echelon form, then we get only 2 linearly independent rows.
Okay. So maybe not everyone knows how to find the row
Hello,
echelon
sir.
form.
I think
Hello.
3,
Yes,
sir.
Dimple.
I think, sir, 3.
3. Rank is 3. Okay, fine.
Yes, sir.
So, okay, fine. So let me ask somebody else. So, Raj, can you tell me what is the rank?
Sir, because all 3 rows are independent.
Okay, great. So, so let me just ask somebody else as well. So, Raj, can you tell me?
Sir, rank is 2.
Rank is 2. Why?
Because if you think that the every elements is different, and there is no non-zero diagonal 0 column in that matrix. So I think its rank is 2 for that. We cannot decompose it in a
whatever phrases you
Hello,
said, by
sir.
that rank should have been 3. By whatever you said, Raj, rank should have been 3.
No, sir, it should be 2.
The answer is correct. Rank is 2. It's not 1 in this case, fortunately. Okay, fine. Thank you, Raj. Let me ask somebody else. So, Saurabh, can you tell me? Saurabh, what would be the rank?
So, if I take the determinant of this matrix and if it comes out to be 0, then we will have to search for lower order matrix which determinant is not 0.
That could have been also 1, right? Rank could also
Yes.
have been 1. That's not. Okay. Okay, you can mute yourself back. Okay, so what we will do is we will look at the columns or rows in this matrix. Say when we are looking at the rows, right? Or for that matter, okay, in this case, let's consider these columns. So one of the column vector would be 210, one of the subspaces 210, other would 5, and the next one would be, these we will call as column 1, column 2, column 3. So you can see that column 3 here has a very simple relation to column 2 and column 1. Right, so you are able to represent one of the columns as a linear combination of the other 2 columns. But you cannot, for that matter, write 2 of the columns as a scaled version of 1 column. So therefore rank is not 1 and rank is not 3, it is 2. Okay, because one of the columns is expressible as a linear combination of 2 columns. So the basis is really the basis set in that sense is only 2 column vectors. Fine. So for such situation, what one can do is, because we are finding column 3 is a kind of linear combination of column 1 and 2, we will write this as a product of the linearly independent columns 2, 3, 1, 4 and 0, 5, right? And try to multiply with a, so if this is 3 row 2 columns, so this is a 3 by 2 matrix, would like to multiply it with a 2 by 3 matrix, so 2 rows 3 columns, so that we get back a 3 by matrix. In this case, you can straight away see just by observation. Say suppose the first A11 or B11 element is 2, right? So therefore we should better have these two elements as 1, 0. That B12 is 3, so therefore this should better be say 0, 1, right? And the third one is going to be, I think, so it is better represented as -1, 1. So we are able to straightforwardly decompose this into a product of a column matrix and a row matrix. So in that sense, it is like I would rather say, yeah, column, because it has okay, so these are having columns with large maybe three members in each of these columns, and row because a larger number of elements along the rows. So that way we are kind of finding it as a product of C and R. So C is straightforward to see. You could have chosen any two of the linearly independent columns in this scenario, but R is slightly non-trivial to find. However, we will soon see that this R happens to be the row reduced echelon form. Okay, so this would be called the row reduced echelon form. Okay, and what is this? Let's just kind of briefly look at it. So suppose we are looking at maybe row echelon form. So let's look at the row echelon form, and for that we can construct matrices. So we can construct matrices like, say, suppose here we can have some numbers like 1, 1, 1, or it could even have been a slightly kind of different number for that matter, but most nicely some 1, 1, 1, and the numbers above this are any typical numbers. So this would be a typical row echelon form. The other version of row echelon form which you can see could be like, you can have a 1, 1, 1, 0, 0, 0. You could have more members here, right? Everything below this diagonal, right, wherever you look at, all of them has to be 0, and above that you have to have a non-zero entries. So these are kind of non-zero entries. So the reduced row echelon form, that has an additional condition, and that condition is that if we have this 1, 1, 1 and the members below this are 0, the members above all of these ones should also preferably be 0. Okay, so that is a criteria. Fine. So even these have to be 0. All members except diagonal element must be 0. Why these kind of forms have a kind of advantage? So suppose this was the coefficient matrix for a set of linear equations, right? So in that situation, the fact that it is dependent only on one of the diagonal elements helps us in finding solutions to the equation straightforwardly. Fine, so that is why this is relevant. The other form which could be kind of seen for this could be like, say, suppose I have a similar situation. Say I have a 1 here. The first member in this is 1, right? Second member could be 1 here. I could even have a kind of once the first member is 1, I can even have a non-zero member here and a 0 later on. And in that case, what would happen is these members are 0 and this could be 1. So this is also a kind of reduced row echelon form where everything above 1 must be 0, but by the side of it, if there is a non-zero number, below that there cannot be a 1. So this is another. So you can, I would like you to, maybe homework would be to read more on this reduced row echelon form and row echelon forms. Okay, this you can look up. What we'll do is we'll make use of this and show you something very interesting about this specific case. So we had a matrix B, right? This matrix B was written as 2 3 1 1 4 3. So 2 3 1 1 4 3. After this example, it would become very clear why we are talking of echelon forms. And what we do is we will make this row transformation to reduce it into the corresponding reduced row echelon form. And that will make it clear that why it is why did we use R matrix which was of this form. Like, could we have simply written it down, or we had to really evaluate it? Okay, so that would be like magic, something will emerge. So in this case, in order to kind of get rid of some of the members, let's do one thing. Like, there are many choices of this elementary row transformation, but let me just start with this one, E12 minus 2. So that would essentially mean that the first one is, there is a minus 8, 3 minus 8 is minus 5, this is minus 5, this remains 1 4 3, this remains 0 5 5. Fine. What I do is I apply R1 E131. So like what I'm doing is I'm adding third column, multiplying it by 1 and kind of adding it to the first column. So that would straight away lead me to 0 0 0 1 4 3 0 5 5. So in order to reduce it to row echelon form, we may have to do some row exchanges. So that we will do soon. But let's just go ahead, continue with whatever comes to mind immediately. So let's do E3 1 by 5. So this is like multiply the third row by 1 by 5. So this is like 0 0 0 1 4 3 0 1 1. Now what I would do is I would multiply it with, so basically I can choose a E maybe 2 3 minus 4. So I multiply the third row by minus 4 and add it to second row. So that would lead me to 0 0 0 and then 1 0 minus 1. and 0, 1, 1. And then I will do 2 row exchanges one by one. So let me just exchange row 1 and 2. So that will lead to 1, 0, minus 1, 0, 0, 0, and 0, 1, 1. And then I do another row exchange, which is R2, 3. And that would lead us to 1, 0, minus 1, 0, 1, 1, and 0, 0, 0. So this is another way of not only getting the row reduced echelon form, but also to say that the rank is 2, because one of the rows has all 0 entries, right? So that just makes it straightforward to say, and the first 2 rows are not kind of linearly dependent, so they're on each other. So therefore this is the row reduced echelon form, and here if you restrict to this subspace, this is what was equivalent to the R above, and in what definition? In V equals to C times R. Right, so therefore you can see that you can do these kind of decompositions very easily if you know what would be the kind of non-zero members. So like linearly independent columns. So you can write down the column matrix and multiply it with the row echelon form of the matrix itself, and that's how you will be getting this version, which is going to be the C times R matrix. So that's again another decomposition which we have seen, and it's also useful many a time. So we have already seen 3 typical decompositions. Let me just enumerate 1 or 2 more. So other decompositions.
Hello, sir.
Yes, yes. Yes, please tell
I
me.
had a doubt.
Yeah, please.
For the square matrices, the principal diagonal is clear. But for the
Okay.
rectangular matrices, just in the second example you have given for REA,
Yes.
with diagonal actually means how do you get these? Is actually
So
the
here the point is, see, Pradosh. So
yes.
the example on the left hand side is straightforward,
Hmm.
right? The example on right hand side is such that, say, suppose if you have a kind of non-zero element on the right of a 1. Okay, so then below that a 1 cannot arise. It has to be 0 all throughout. So what I mean is these must be 0 if this is a non-zero element. So this is a non-zero element, and it still remains a row reduced echelon form. So basically what happens is, in many kind of physics problems and actually applied maths problems, many a times you would not be able to reduce matrices into subspaces beyond a certain limit. Okay, so when I say like reducing a large matrix or partitioning a large matrix into subspaces, what I mean is there would be fairly large sections which would be 0, and in between there would be some sections which would be essentially square matrices or rectangular matrices. Okay, so in certain circumstances you would end up into scenarios where you will have a non-zero element hanging around. But as far as the number below that is 0, all numbers below that is 0, there is no 1 below that. So that is fine. And then that is still called a reduced row echelon form. Okay, and I would expect all of you to read a little bit more from any linear algebra textbook that you see. You have to understand that in a PhD course, it's mostly what you do is what is going to help you in later part, right? Classes are a very limited portion of the learning process, right? There are only a finite number of classes happening on every topic. So you will have to read and of course come back with doubts wherever you have. Okay, and I would just like to kind of for sake of completeness mark other such decompositions, and I would like to particularly take up this idea of singular value decomposition because that is very, very important nowadays. Like whether it's an optimization problem, whether it is kind of variety of physics problems, principal component analysis, like in variety of areas, the knowledge of the technique of singular value decomposition is going to be really useful. Like that really brings about a lot of insights. So I would like to talk about that later, but first let me try to summarize what all other such decompositions are, and that would really help us. So let me just enumerate some of them. So other decompositions. So one of them is called the QR decomposition. So I am trying to balance out things between what we do here and what we will be doing in numerical techniques. So later on, we will be taking this up maybe in the numerical techniques instead of the LU decomposition. Okay, because that would really help us. So here, Q is a, like as we just saw, it is orthonormal, means it is composed of orthonormal column vectors, and R is going to be an upper triangular matrix. Okay, so that is one, again another, like one particular decomposition which is of interest. The other decomposition which is of interest is to write A as x lambda x inverse, where x has eigenvectors of A as columns. Okay, and lambda is essentially the eigenvalues of A along diagonals of
Hello, sir.
diagonal. Yes, hold on just a second. Along diagonal of lambda. Yes, please tell me.
Hello.
Yes. Hello. Yeah, please tell me. Hello, please tell me. I am able to hear you. Hello. Hello. So I will presume there is no question because I would not like to kind of lose track of, yeah. So I think I will continue. Maybe if there is a question when you connect later, you would be asking again. Okay, the third very important decomposition is to write A in the form of a matrix product, which is like U sigma V transpose, and this is what I was referring to earlier, like this is called singular value decomposition. First, let us know what it is, and later on I will come to like why it is relevant. So it's applicable, first of all, it's applicable non-square matrices as well. So it is applicable to square matrices as well as non-square matrices. So that's very relevant, because all the time you are not going to come across square matrices only. So let me just see if somebody is hanging around in the lobby. I hope he will join. So this is one of the perils of online teaching, where you will have to keep track of many things. In a classroom, when we are typically doing teaching learning sessions in classroom mode, like offline mode, so then I typically allow my students to leave the class or come in at any point of time, but use the back door, not the front door, and do it without disturbing anyone else, like to the extent possible. So any drinking water, any phone call or anything. So these kind of luxury, we are not really able to encourage so much in these kind of online forums, because every time you move out, it means for getting in you need a permission. And if I don't put the security measures, then like there are, of course, like for example in Zoom, there is Zoom bombing. Even Microsoft Teams, we faced issues earlier. So that should be avoided to the extent possible. Okay, so first of all, this A can be a non-square matrix. So that is, it can be a rectangular matrix. These like U and V are orthonormal, or contain, U and V contain comprise orthonormal singular vectors. It will become much more clear when we see it soon. And these singular values sigma 1 to sigma r, where r would essentially be the rank of the matrix in sigma. So we will singular values sigma 1 to sigma r exist in S. So let's see how we are going to write it. So let's like to begin with, we understand that we have written this. So let's do this third one in some more detail. So what we'll do is more details on okay, so let's do some more details on SVD below.
Sir, I had put down.
Yeah, please tell me.
Sir, it's like, why are we focusing more on the orthonormal vectors or orthonormal matrices, as in A equals to QR, also we take Q as orthonormal.
So okay, so it is relevant. See, we will see when we see some physical examples from applied maths and physics. It's much more convenient to work in with such vectors. Okay, so that's why a large part of, so whatever we have enumerated, right, in a sense, like applied linear algebra is more or less like whatever decompositions we have mentioned. Even for doing deep learning, more or less with this much background, you should be able to do all the necessary maths. Of course, SVD we are developing right now. It turns out that's more convenient, right? And let's see as we move along. Okay, we'll have better answers to these questions coming from even the student side. Okay, so what we'll do is,
Sir?
when we are writing this, yes, please.
Sir, is there any particular name of the second decomposition?
Second deposition, singular value decomposition, or the CR
no,
decomposition.
above this singular
No,
value
CR decomposition. We call it CR decomposition. Okay. So basically, you are putting it into row echelon form, reduced row echelon form, the row matrix, and the column matrix comprises of the linearly independent columns only. Okay. So here this U and V are respectively. So U I can say as the left eigenvectors. So suppose A is a M cross N matrix. M can be equal to N also. So typically we'll do an example which would be M equals to N, and we will have problems where M would not be equal to N. So here, like U would be composed of left eigenvectors in Rm, and V would be composed of right eigenvectors in Rn. Okay, and like what we'll do is, one can say when we have this A is written as U sigma V transpose, one can multiply this, like operate this on V, and therefore, so let's just mark it V as we are marking. Okay, so that would be equal to, so U sigma V transpose V. So we have a very special for orthonormal vectors, like this is kind of identity, and therefore one can write for the corresponding column vectors, which we'll write by the script letters. A V would be sigma U, where sigma would be the corresponding eigen values, or in a manner what one can do is one can write this A on V1. So V1 is one of the orthonormal eigenvectors comprising V. Okay, so AV1 would be sigma 1 U1. That is what it means, and so on until AVR equals to sigma RVR UR. Okay, so V is connects to U and U is connects to V, and beyond this, A V R plus 1 equals to 0 up to maybe A Vn equals to 0, so on. So here, one other point to be noted is this proper ordering of these eigenvalues. So sigma 1 is always greater than equal to sigma 2 is always greater than equal to sigma 3 up to sigma R. And this should be greater than equal to greater than 0. Yeah. So these are the thing. And last, N minus R V's are in the null space. So they are as good as 0 vectors. Okay. So now this left singular vector. So these are just some of the properties which I am just illustrating. So left singular vectors is happening here. Let's see what's the message. No, there's no issue. That's fine. Oops. So left singular vectors u1 to un or go in the columns of u. So that is crucial. And we also have V transpose equals to V inverse and U transpose equals to U inverse. And that also tells us that this AV that we had, right, that is also U sigma because V transpose for here. We have a back-to-back power trips here, but I hope because I am connected to online, I think, yeah, so I think we are not disturbed as yet. So we can write this as U sigma, and I think we still have 15 minutes for 3, so let us just try to complete this. So therefore, this particular form can be expanded to write A times, so V1 VR Vn should be equal to, we'll have a U1 UR UN multiplied by, we'll have a vector which would like a matrix which would be sigma 1 up to sigma R.
Hello, sir. Screen is not visible, sir.
Remaining to be, huh? Hello.
Hello, sir. Screen is not visible.
Oh, I see.
No, it's visible.
I think it is because of the.
Sir, it is visible.
Maybe,
It
sir.
is
Visible means
visible,
the
sir.
internet on.
Okay,
Yeah,
then problem on my side, sir. Okay.
Please be a little more. So otherwise we will be accidentally stopping the video recording. So let's not do that. Later on you can have a look at it.
Okay, sir.
Okay, so I hope that it would become better. You try to check your internet connection. Okay, so this is how we are going to write this, like this particular relation. AV equals to U sigma could be written like this. And whatever is written on the rightmost end, where we have written sigma 1 to sigma R along the body diagonal, remaining are all 0 members. So all the so when I write a capital 0, it's like all the other members are 0, all the other entries are 0. And then that's the subspace with R by R kind of a order. And then there are zeros everywhere till n, nth order. Fine. So The interesting thing about this is, like, one can talk in terms of pieces of singular value decomposition. So A can be A, which is otherwise written as U sigma V transpose in its grand matrix form, could be written down as an expansion where you can write it as sigma 1 U1 V1 transpose plus so on till sigma R UR VR transpose. So the beauty of this expansion is the contributions become less and less important as we proceed towards the right. So sigma 1 U1 V1 transpose will contribute the most. Sigma 2 U2 V2 transpose will contribute much less compared to sigma 1 U1 V1 transpose, and so on. So of course, the like larger the number of terms you take, more accurate would be the result, close to A. However, like, you are not doing a very bad job by ignoring some of the members. So this technique is particularly very useful in its higher dimensional version when we are looking at large databases. Say large databases, say suppose there's a shopping platform like XYZ, and it is keeping track of purchasing patterns of each of the individual subscribers it has. And it is looking at what is the pattern across the 30 days of a particular month. And then within a month, what is the shopping pattern from morning to night? And then because this would primarily be guided by when the person is getting a salary, when he is getting some bonuses, etc. across the month. And then how is the earning pattern? Earning pattern is not identical for all the members of the society. There is a very small fraction which are salaried class people. Most of them are kind of doing some kind of work which is not a typical salary equivalent scenario. So therefore, like, the shopping platform can keep track of all this information depending on old buying patterns of a large number of individuals, and then construct these matrices and then plan out like which portion of the day it has to kind of bother about putting its resources for that individual person's computation. So for example, like shopping portals do give you a lot of hints about what you should buy. These hints, if they are trying to continue evaluating all the time and giving you hints all the time, that would be highly computer intensive. So they would like to give it at the right instant of time when you are most likely to kind of be enticed by that offer. Okay, so similarly, like many ad suggestions, the sites you visit, how that, like how the next suggested site would be there, like the kind of content that we watch, depending on the suggestions which it is going to throw up. So suppose if you are watching a lot of contents along platforms like edX, right, which is an educational platform across all disciplines. So after a while, it will stop giving you suggestions from non-related areas. So it would be able to figure out which are your related areas. And in all these, at some level, SVD process is happening. So that's why kind of it is very important. Okay. So like, because the rows up to a particular kind of number are only relevant, because beyond that the sigma r's are 0, right? Beyond that, sigma k, if I say sigma k or k, sigma k equals to 0 for all k greater than r, right? So therefore these becomes irrelevant. So therefore one can also talk of this reduced SVD. And over here, what basically happens is you are kind of acting on VR, and you will be kind of getting into UR sigma R. Right, so that is equivalent to maybe writing A into this V1 to VR. So I'm just rewriting a portion of that VR, and then that would be equivalent to U1 to UR. These are all column vectors, and then sigma 1 to sigma R. So we don't have to really bother about rest of the irrelevant scenarios. And this VR transpose, just hold on, equals to UR transpose UR equals to identity R. So, okay, so at times I'm interchangeably using capital V and small v. If that is the confusion, that should not be. We are primarily looking at the individual members. So, yeah. Okay, yeah, please tell me, Pradosh.
Sir, I guess Babaji is in the lobby. Just message me.
Oh, thank you for that. But he was very much there in the class. I think he left in between. Yeah, he's been added. He's been added. Okay, so let's try to do an example, and that would illustrate this process. So let's try an example. So I think we don't have so much of time left, however. So what time your next class starts? Hello, what time will your next class start?
Yeah,
On 3 o'clock, sir.
3 o'clock, right?
3 p.m.
Okay. So let's see how much we can do in next 5 minutes. So let A be this matrix, which is 6, 0, 8, 10. What I would do is I would urge you to obtain these matrices like A transpose A, and you can write this as 6, 8, 0, 10, 6, 0, 8, 10, and that will lead us to 100, 80. These are simple matrices, so not very difficult to do this multiplication. But why we are obtaining it will become clear, why we are obtaining this AA transpose and A transpose A. So AA transpose is going to be 6, 0, 8, 10, and 6, 8, 0, 6, 8, 6, 0, 8, 10, and 6, 8, 0, 10. Is that the factor? 6, 8, 0, 6, 0, 8, 10 and 6, 8, 0, 10. Yes. That is going to be like 36, 48. This one is also 48, and this is 164. One interesting thing to check would be if you sum the diagonal elements, that is trace of these A transpose and A transpose A, that should be identical, and that it is. So it is 200 each. That's just a quick way to check that there are no issues or no problems here. So eigenvalues of A transpose A or AA transpose R. So you can find it by the method like determinant of A transpose minus lambda identity equal to 0. Right, and you can see that these are going to be like these eigenvectors are going to be 180 and 20. Right, this is a straightforward calculation, but please do that. The reason why I am trying to kind of do these kind of transposes is to just rewrite this expression again. So we had A, which looked like U sigma V transpose. So therefore, suppose I am obtaining a quantity which is AA transpose. So that is like U sigma V transpose V sigma transpose U transpose. Right. So that is equivalent to U sigma transpose U transpose. Right, because V transpose is going to be 1, and because this sigma is a diagonal matrix, so therefore the sigma transpose is going to be like whatever is the eigenvalues, you are going to square those eigenvalues along this. So this would be typically of the form that you will have this written as U, and then there would be this and so on, and V U transpose. Right, so that is what you will end up getting. So therefore what happens is, now if you apply U on it, right, so this simply implies that, so let's just partition this part just to make sure that you are able to see this. This simply implies that you can write AU, AA transpose U would be essentially U sigma square. So suppose I am looking at a particular vector in this, so I can be more specific about this. So AA transpose U1 would be sigma 1 square U1. Okay, so therefore what happens is, all the U eigenvectors are eigenvectors of AA transpose, and similarly you can see that all the V eigenvectors, like which are composing V matrix, they are eigenvectors of A transpose A. So therefore A transpose and A transpose A were supposed to be obtained, and like for AA transpose, you can see that the eigenvectors are going to be V1 equals to 1 over root 2 1 1, and V2 equals to 1 over root 2 1 minus 1, and similarly for A transpose A, one can find that your V1 is going to be, U1 is going to be 1 over root 10 1 comma 3. This you can check for yourself. This is an interesting exercise, and this is going to be 1 over root 10, then this is going to be 3 comma minus 1. So like as soon as you obtain this eigenvalues and eigenvectors, so this is corresponding to an eigenvector which is root over 120 180, and this is eigenvalue, and this is corresponding to an eigenvalue. So eigenvalues are, these are the eigenvalue. So corresponding to eigenvalue, okay, so let's put this here, eigenvalues. So what we are talking about is eigenvalues root 180 and root 20, and they will correspondingly have eigenvectors along the columns here as 1 over root 2 1 1, 1 over
Sir,
root 10.
why 180 root over, sir? It may be 180 and 20 eigenvalue.
That is for AA transpose, and what we are talking about is corresponding to A.
Okay.
Right, or corresponding to, so like basically sigma 1 square. So maybe what we can do is we can write this as, instead of, yeah, so not a bad point what you mentioned. So we can write this as the corresponding sigma 1 and corresponding sigma 2. Okay, sigma 1 square and sigma 2 square are the eigen values, right? That's what we saw. So now with this, what happens is you have to simply write this matrix. So therefore, now we can do this singular value decomposition, which would be like sigma 1 u1 v1 transpose, which we wrote, plus sigma 2 u2 v2 transpose. So that is what is the expansion. Okay, and that is like we can see that we can have root over 180, right? U1 is going to be U1 and V1 transpose. So U1 is going to be 1 over root 10. Okay, so 1 by root 10, and then it's going to be 1 3, and then this is going to be 1 1, and there is a 1 over root 2 also, because 1 1 comes with a 1 over root 2. And similarly, you will add up another term, which is root over 20 divided by root over 2, 1 over root 10. These are the factors which are there. You have a 3 minus 1 and a 1 minus 1. Okay, so that would add up to, that's going to add up to 3 3 9 9 plus 3 minus 3 minus 1 1, and that would, like, if you add these two, this is basically 6 0 8 and 10. So here it was only a 2 by 2 matrix, but still the contribution from the first term is more significant than the contribution from the second term, and this becomes more and more obvious if you are handling larger sized matrices. Okay, so in such situations, what will happen, and larger dimensional objects. So in such situation, what will happen is your first term may have order of magnitude larger valued quantities than the second term, and so on. So as you proceed to higher and higher terms, the contributions will become much and much less significant. So that is kind of crucial about it. There is an interesting geometrical interpretation to this also, which we will come to later in the next class. So we'll have a tutorial session on Thursday. So we'll discuss more about these things.